Second part, I'd like to talk about let me first start from an experiment, like using nosy as example. What do we do to make sure that we get the best out of a spectrometer? Um, and the reason I use nosy as example is that it's the most challenging experiment, really, in terms of um, reconstruction data. So here is a 3D nosy chosy that I'm showing you. Um, First thing that I want to point out is that it's my practice. I don't know that people it's debatable, okay, but my practice is always try to minimize the number of scans to maximize the number of FID to be recorded, because I consider every data points, every FID we collect as additional information for the reconstruction. So the more data, the more number of points we collect, the easier the reconstruction should be. And in order to do that, sometimes that we run a nosy chosy 3D, we even want to do only 2 steps phase cycling, number of scan 2. And the problem for that is this. Looking at this nosy chosy pulse sequence, for example, if I do 2-step phase cycling, we have 2 choices, even phi 1 or phi 2 here. Now, this is the echo anti-echo using the gradient, it's gradient encoded, gradient selective experiment. Therefore, you don't really need phi 2 phase cycling for the T2 dimension. Okay, therefore you're left with phi 1. You could just phase like this. The problem is that if you phase cycle a proton without phase cycling any nitrogen pulse, there is no heteronuclei filter. Therefore, water suppression is a little harder to do, right? And water can cause baseline issue and all kinds of issues. And therefore, this is not recommended. So when I do 2-step phase cycling, I still prefer do phi 2. Okay, so the water is clean. Then the problem is this. If you don't phase cycling phi 1, the problem is that there is a something called axial peak, which is 0 frequency peak, that caused by mostly the T1 relaxation during the mixing time, and the pulse imperfection of phi 1, of course. So the other thing is this: if these axial peak are not removed, and they could be very strong and out of phase. And for SMILE, that's killing, I have to admit, because if peak is not absorptive, the reconstruction will not do very well. So here's how I optimize this. I want to use this example to show you what kind of effort that we put whenever we collect a good data set. Is that we do 2-step phase cycling so that we could acquire as many data as possible. And then we make sure that the axial peak is ying phase. And to do that is that we cannot use 90-180 phase correction, meaning that we should not have a delay for the first time point of T1. So there I put an echo here, the 180 composite pulse for better IF offset performance and also for reducing the IF inhomogeneity, the impact of our IF inhomogeneity. It's not going to improve the IF inhomogeneity, okay? So therefore, you don't have linear phase correction. But for the composite pulse, you need 2 of them because otherwise it causes phase distortion. So we do that in pair, apply this at the end of it, okay? So that's nice. Another problem is this. If you just do this, you'll see that this axial peak is 45-degree phase shifted. The reason for that is that axial peak in this case mainly dominated by the T1 relaxation during mixing time. So whether this phi 1 is real or imaginary, meaning that you either acquire sine or cosine, the same amount of T1 relaxation you get. And therefore, the real and imaginary part are equal. So therefore, it's 45 degree. And so your phase, your peak is out of phase by 45 degree. And that's a bit of a problem for me. So to do that, the good news is that the axial peak is not sensitive to the phase of this pulse, while the peak is completely determined by phase of phi 1. So what I did is that I phase shifted 45 degree of this pulse. And therefore, everybody apply 45 degree phase shifting, phase correction, and everybody in phase, as you see here. Now, I have to admit, this is a short mixing time. I don't know which data set, but it's short mixing time, and it's quite a low low temperature. So the solvent exchange is not that fast. Therefore, the axial peak is not really much stronger than the diagonal peak. Otherwise, I probably will have to do four-step phase cycling. Okay, so that's one thing. The other thing is that I always do set larger spectral widths in the direct dimension. Here I extracted, of course, but I always set it to be larger. The reason for that is that in case you have a baseline issue, so if you have larger spectral width, then you have larger empty baseline segment that you can use for more reliable baseline collection before any reconstruction. Okay, and of course, if you could keep baseline as flat as possible so that you don't need baseline correction, that would be the best. And that involves good water suppression. And for cryoprobe, it's not easy sometimes. And for us, lucky that we have a few probes of cryoprobes that have triple axis gradient, XYZ gradient, so that we could use, for example, these decoding, encoding pulses. If we set them to use all the XYZ gradients, the water suppression usually is very good. Okay, so I guess for this, I cover every point here. Okay, so now let me show you an example of 4D experiment. One is HMQC, nosy, chosy, and the other one is chosy, nosy, chosy. Okay, in this case, if you want to do 4-step for 4D, it's not unreasonable. Okay, but if you want to do 2-step, which phase cycling, which pulse should we phase cycle? I tell you, for HMQC, if you want to do 2-step, you like to want to phase cycle phi 1 over here. The reason is that it has to be 2-step, is it has to be nitrogen so that heteronuclear filter is utilized and water can be filtered. And so in the end, you get a better solvent suppression. The other thing is that by phase cycling this guy, the axial peak that caused by T1 relaxation due to mixing time is removed, because by phase cycling this guy, your signal, even though you're not directly phase cycling the proton, either here or there, your signal is still going up and down depending on this phase, okay? Well, the axial peak is always pointed up. And when you phase cycle this guy, the receiver also goes up and down. So axial peak is canceled because it's always positive and the receiver goes up and down, positive and negative. So they cancel. However, by phase cycling this pulse, the pulse imperfection of the 90 could still give you a little bit contribution of the axial peak, but I expect that to be very weak. Should not be a problem at all, okay? And this chosy, as I said, it's echo anti-echo, it's gradient enhanced, so you don't need a phase cycling this guy. It's supposed to work just for single step, all right? So this is a better way for HMQC, and for 4-step, if you want to do 4-step, I will do phi 1 and phi 2 without phase cycling phi 3. Then you should be able to completely suppress the axial peak. Now, when you do chosy, nosy, chosy, again, I, hold on a second. I think in this case, I would also pick up phi 1 if you want to do two-step. But if you two-step, four-step, you do phi 1, phi 2. Okay? Now, the reason I bring up the CHOSY, NOSY, CHOSY is that you can see there are two indirect dimensions that's collected using echo anti-echo. Okay? As you know, whenever you use echo anti-echo, you have to reshuffle the gradient. You have to take the sum of echo anti-echo and take the difference and then phase shift it by 90 degrees to get the right, to convert basically phase modulated data to be amplitude modulated. Okay, so it actually, when I run this, it was like an adventure because I couldn't get the data correctly, particularly on top spin. When I tried to look at the plane of T2, F2, and F4, whenever I run a multi-dimensional experiment, I always test the plane. So when I run F2, F4, or F1, I forgot F4. I believe it's F2, F4, okay? That I could not get the data correctly within top spin. No matter what I did, it's not. And the problem shows that clearly it's a quadrature problem. And the reason is that when you use echo anti-echo in the indirect dimension like this, the reshuffling of the FID is no longer along the direct dimension, okay? It's really the reshuffling of the FID along T2. So you collect the echo and anti-echo of this, and you get a 2 FID for T2. You should shuffle over there. And I unfortunately don't have example for that today, but with something, you don't need additional program, just with a little bit of manipulation of the matrix. So when you do this, you make sure that direct dimension x-axis the NMR pipe is T4, then you apply echo anti-echo. And then when you do indirect dimension, you make sure that you convert it, you transpose the data set so that T2, F2 is your current x-axis, and then you apply echo anti-echo to the T1 dimension, and you'll be okay, all right? So next thing is baseline. Okay, no matter how careful you are, some of the experiment, for example, some of our pressure jump experiment, it's very hard to do the baseline, to get a straight baseline, because imagine during the experiment, you actually apply very high pressure, you know, and then when that pressure changes, a lot of vibration and this and that, and also screw up with the lock and you know, shim and things like that. So it's harder to do water suppression, and therefore it's also it's almost impossible to get a flat baseline. So I started using a polynomial NMR processing function, poly, to do that. But sometimes it really doesn't work that very well, particularly for something very dense like this. And when you apply poly, it tends to like sink down like this. It's still, you know, a little bit polynomial, like second order polynomial there. So we actually noticed there's a program published a long time ago by Gunther and Wuthrich. It's called a FLAT. So what this does is really try to discover what is the baseline, what is the peak, and then fit it to the baseline, and then do SVD to figure it out. What are the first few data points in the time domain that caused this problem? So basically, is just do inverse Fourier transform of these baseline segment, and then ask the question, what is the time points corresponding to those baseline distortion? And therefore, you subtract those time points from the real data, you get a flat baseline like this, okay? So we use it for the time domain data of the direct dimension is fully transformed, and usually the signal density is high, and the baseline is limited. But if you acquire more spectral width, it helps you to run this flat baseline processing function. And by the way, if you get the latest SMILE, it has flat inlet, and you can just do something like that. And usually it's optimized to the convention case that you don't really need to add other parameters. The default works for most of the cases. And if you, the only thing you need to do is that if you apply this to the whole full spectrum, you really need to make sure that extract the upfield limit. For example, 6 ppm, the left one, X1, it goes to 12, 13, or whatever you have. I don't extract it because you want to have as many, as much segment, as large a segment as possible for the baseline. So you only need to extract the other part. And sometimes I also put another option called dash first, dash last, meaning that the first and the last segment and the first segment is always considered as peak, okay, as a baseline, and should be used for baseline. This works if you have something like a little bit like artifacts, and the program may miss it and may think that as a peak and miss the edge, and therefore the reconstruction may not work, particularly on the upfield region. Usually it's very small, from 6 ppm or 5.5 maybe to 6.5, depending on your most upfield peak. So one application that I didn't talk about it in the first part is that doing resolution enhancement. No, I didn't talk about it, yes. So in this case, an example is a C13 constant time. And as you know, we do 28 millisecond in the carbon dimension, so the C alpha, C beta coupling is suppressed. So either do 28 or 56 millisecond. This is 56 millisecond real data, okay? And we try to do couple to make sure that carbon dimension is coupled so that we get the quartet. It's pattern of 3 to 1 to 1 to 3 for HSQC, not 1 to 2, not 3, not 1 to 3 to 3 to 1. So either we do 28 millisecond or 56 millisecond, but 56 milliseconds, sometimes they lose a lot of signal. So it's not doable. So in this case, we do 28 millisecond, and we try to extend it to 56 millisecond. And this is a 28 millisecond with a kind of cosine window that applied up to 58 milliseconds. So part of the resolution enhancement coming really from the more aggressive window apodization function that we use. And then you can consider these as the special non-uniform sampling artifacts that cleaned it up by SMILE. So that's one way of doing it. And in the past, we use linear prediction, but now I think people, at least we use non-uniform sampling, treating the second part of FID as a special non-uniformly sampled data and reconstruct them. And this is, of course, goes back to the early way, and Jeff and did it a long time ago too, was a maximum entropy. Okay, so another application is that you could use non-uniform sampling to fix bad data points. So here it's, what is this? Oh, sorry. Hold on. Okay, so you could use that to fix them. So here is a Bruker display for all the FIDs that are corrupted, and some are good FID, of course. So it's just one FID after another. And I extracted the worst FID, fully transformed them, you see in blue here, relative to the first data points, which is good. You see that somehow my magnet shifted the frequency by a couple of hundred hertz, and therefore the water suppression was completely messed up, and give this kind of corrupted FID. And by the way, we did a lot of stuff to fix it, but we never know what we did fix it. In the end, it just went away. Okay. It may also possibly related to some of the reconstruction work that's going on near the magnet, outside the magnet room. So anyway, so I'll show you in the demo, I'll show you an example how to do that, to fix this kind of bad data points. And this is the directly fully transformed without fixing those bad data points. And these are the one that fixed, with the bad data points fixed. You see the actual peak is still pretty strong. In this case, it's not my data. It's some other users send it to me later. Now I like to talk about, actually a big chunk of my talk will be focused on something called random phase or random quadrature detection. It's initially proposed by Mark and Jeff, okay, and later, and then Mark and Jeff first call this kind of data random phase detection, I think, right, or partial components. And later, Needle Spark, 2 years or 3 years ago, they proposed to do this random quadrature. So let me clarify. In my eyes, they're really almost interchangeable, but with random quadrature also applicable to echo anti-echo instead of just cosine and sine component, okay? So when I say this, I really means random RPD and echo anti-echo, okay? So here's an example. If you do conventional NUS, you always assign, if you pick up a time point, you always sample both real and imaginary, okay? And this is fully transformed. You see that the artifacts is somewhat symmetrical, right? It's not as randomized as we might want. But if you do RPD or RQD, you pick up those two components relatively separately, and you make sure that there's no overlapping. You get something like that. At least it's no longer symmetrical like this. And that introduced more randomization into the sampling schedule and the artifacts. And talking about randomization, you can look at the Adams paper in 2015. So although when I look at this problem, I think that mathematically the real and imaginary is independent, okay? The information there should be independent. They are not redundant. But I believe what the Adams said in the paper, that it should make it more random, introduce more randomization, and should be a good thing. So particularly after the needless paper, I thought it was useful. So I went ahead and implemented this in Smile. And first thing I did is that I have to come up with a new format for the sampling schedule. In the end, suggested by Frank, that I have a header like this. Luckily that Bruker doesn't skip this thing if you have a hash. And the first column is a y increment, and then you have a y quadrature. So 0 either for cosine, 1 for sine, or 0 for echo, then 1 for anti-echo if you do sensitivity enhanced. And the z dimension for 3D, you have z column for this column for increment and this column for phase, okay? And I have a tool, RQD sample.py, that comes up with something like that. And if you download Smile latest version, you should have this already. Now, it's a little bit complicated when it's a phase modulated. I'm not going to go through the details, but the thing is that the math is simple. If you have echo, I think it's also called N-type. I may messed up, okay? You have something like this, okay? In the real part, in the hand, in the real FID, you have a mixture of both real, like purely absorptive, and also purely dispersive, okay? And same thing for this. And usually we do the combination when you tell NMR conversion script that this is echo anti-echo. What it does is that you really combine those and you get the pure cosine modulated. And if you take the sum followed by negate the imaginary and adjust the phase, you get a sine like that. So therefore you convert the phase modulated to amplitude modulated. But when one component, either echo or anti-echo, is missing, what happened is that when you do you still do the recombination, okay, the shuffling. But in the end, the problem is that your spectrum still has purely absorbed like this and purely dispersive, okay? In the real and in the second FID of the indirect dimension, you get a sine modulated absorptive, but you get a cosine modulated dispersive. When you have anti-echo only, you get something similar. Basically, it's a mixture of purely absorptive and dispersive. Okay. The good news is that you see the sign of these components does not depend on whether you take echo or you sample anti-echo. But the sign of those components we don't want actually modulated by which point you pick, okay, which component you pick. So if you randomly select echo, anti-echo, then those signs are randomly modulated, those terms. And as a result, they actually spread it more than the purely absorptive component. And as I show you here, for example, I have 512 complex data points in the indirect dimension. And if I keep 512 endpoints is echo completely and set the anti-echo to be 0, I get something like that. But if I do the opposite, I get something like this. Notice that the sign inverted because in the previous slides, the sign is inverted, okay? And if you add them together, you get the sign in the middle doesn't change, you see? So all the sign that flipped it canceled and the sign in the middle doesn't change and you get a good spectrum, okay? That's corresponding to the completed sample. When you don't have a completed sample, if you randomly pick 256 N-type and 256 P-type, you see that the peak, the purely absorptive peak is actually not, of course, it also distributed, but majority of them is concentrated here. But the dispersive one, actually, majority of dispersive components are spreaded as a noise like, okay? And therefore, SMILE works. Otherwise, SMILE will not even work, okay? The problem here is that the artifact is really dispersive, okay? So therefore, make the baseline collection is a little bit harder because dispersive is broader and traced out and may be considered by a baseline collection program as noise. And so anyway, so here's how SMILE reconstructs. When there's echo but without anti-echo, SMILE always reconstruct as a cosine and sine. But in the data, in the input data, SMILE, the input data, it's really a combination of cosine, the cosine modulated absorptive and sine modulated, purely dispersive. And so imaginary, the second FID in the indirect dimension is like this, right? So what SMILE does is that it always reconstructs the cosine and sine component, but then try to from the sine and cosine, reconstruct the data that's in the input data and then subtract it to remove each peak. And whenever the peak removed and also the artifacts associated with peak, including the artifacts which is dispersive. And when the other component is sampled, SMILE does this. reconstruct cosine sine, recombine this cosine and sine to get this kind of data set, and then reconstruct it. And to use that for this kind of data set, what you need is really just tell which dimension is echo anti-echo, and you do dash XEA, and then depending on which indirect dimension. And for now, direct dimension was partial component of echo anti-echo, but it could be any indirect dimension, okay? And whenever data is done before SMILE, it has to be reshuffled. Even though the echo or anti-echo is missing, you still reshuffle them. The other thing is that, like I explained, we reconstruct cosine sine, but then we recombine to form phase modulated data, because that's what in the input data. That's how the program cleans up. And the downscaling factor is different from without the echo anti-echo. And the baseline is a little bit harder to do. And I actually applied this to a NOISY spectrum, a fully sampled NOISY, high signal to noise. I think it's the same NOISY that we used for NUSCON competition. The red dots are the ones that detected either in RPD or RQD, but not in the conventional data. So yes, RPD or RQD does do a little bit better, seems to be a little bit better than the full components. But unfortunately, the peak fidelity is actually comparable for RPD. I think for RQD is slightly worse. And I think that if you look at the peak components in the peak, so the line shape probably distorted to some extent, that might contribute to this kind of results that we see. And basically, that's a summary that I've already mentioned. Let's see. Yeah, RPD is a little bit better. RQD is actually slightly worse. So when you do echo anti-echo, I don't recommend you to do the partial component thing for echo anti-echo, particularly if you have a baseline issue, okay? The thing that RPD, RQD that I like is that it makes the post program simple. I didn't say, but you might not know that most of our spectrometers still running top spin 2.1, which, as you know, doesn't do non-uniform sampling. So we always hard code our post program to do the sampling, to do the non-uniform sampling experiments. So with RPD, RQD, the programming becomes easier because I don't need to code the loop for real imaginary echo anti-echo, because what I need to do is just read it out from the sampling schedule. So that's what I like. So now if I need to code an experiment for NUS experiment for top spin 2.1, I always do RQD or RPD type in the post program, but I can feed it with a full quadrature, full component sampling list to the experiment. So still using the RPD post sequence, but run either RPD or FPD, I call it, full component or full phase or whatever, full quadrature detection, okay? And we'll have a few post sequence to show you later in my demo. Here's a few updates for the current SMILE version. It's compatible with the older one and can do RQD or RPD. And it supports new format of the 4-column for 3-dimensional, 6-column for 4-dimensional RPD sampling schedule. And also recognize the older one, traditional 2-column for 3D and 3-column for 4D. And there's a utility that's included in the program if you install the latest one. And I'll cover those in my talk, in my demo later. Another thing about Bruker thing, I don't know anything about variant, but for Bruker, I want to point it to you something that I learned. There's a parameter called NUS SP type, and it's not in the EDA parameter space. you have to type it in. And depending on setting of that parameter, you get very different sampling schedule, okay? If you set it to 0, it's no repeat shuffle up to 75, meaning that it's default, okay, 0. Meaning that if you do 75 or less % of sampling, you don't have a repeat. But if you do more, you get a repeat, okay? If you set a 1, it's regular, it's all value between 0 and half. If your TD is 100 data points, it's 0 to 49, it could repeat. Oh, I don't know. I don't even know what this means regular, actually. I forgot. The 2D, if you set it to 2, shuffle, means that repeat is always allowed. It doesn't have to go to 75%. The repeat will allow. So if you set it to this, it will repeat. You will have duplicates in your sampling schedule, meaning that same time point, we collected twice. If you set it to 0, there's no repeat. And even to 100%. If you set to 4, you get a % gap. It only works for top spin 4, I think. Okay, and because of this repeated stuff, and in SMILE now, we have an additional flag called dash sample average, so that there's a repeat, we can average that. But the good news is that Frank already takes care of the average in the during the NUS expand, the script that you use to expand the data. Okay, now I don't know the literature enough whether this kind of repeat, what's the advantage that is. Maybe Jeff can help us understand it later. He can comment on it. Jeff, are you there? Well,
Here,
No,
Jenfa.
I believe he
Yeah.
stepped out.
Yeah,
So-
no, right here.
Oh, no, back in.
you here?
Yes.
Okay, so some sampling is of doing that.
You know, we still don't know
Okay.
for sure, Jenfa. It actually is something that Yulia Postovalova
Okay.
is working on actively
Okay.
right now. We could, maybe at the end, we can discuss it.
Okay, yeah, I naively think that the repeat has redundant measurement, and I thought that you know, if you don't make a repeat, we have more independent measurements. But one thing is that, like Ed said to me, he said if you throw a bunch of bean or corn to different place, some are fall into the same can, some are not. So it sounds like it's a more random process. But anyway, I prefer not to repeat, but certainly it's a possible in Broca standard data set, okay?
So just
Sure.
one quick comment on it, Jinfa.
Yeah.
The problem that we face is most of the codes, including ours, the way they deal with repeated measurements is you would have to add them together.
Oh, I see.
But you know, from a Bayesian's perspective, you'd be better off keeping them as separate measurements.
Okay, I see.
And
Okay. So more options here. Thanks, Jeff. More option here. Mimic what the NMR piper does. If you have a column sequence, first column T3, second column T2, and third column T1, if you do opposite, you now can use sample reverse. And if you run SMILE for some of like the cluster that you have limited amount of time, you could use dash max time in case the experiment runs before your time is up. You make sure that even SMILE doesn't finish, does not converge, you will stop and save your data, exit before your time is up, okay? But when you do that, if you, let's say, have 24 hours of your cluster time, make sure that you also give a little bit of time for saving and you know, like the I/O of the data. These are not considered because SMILE doesn't know before and after how much time it needs. And there's also SMILE stop. If you run a 4D, long 4D, and it takes like a long time, but you feel like it's enough, or you feel like I want to see the data, what it is now, and you can just create an empty file like this. The program will keep checking it for each iteration. If it sees it, it stop and wrapped it up and then export the data. so that you don't have to kill it and lose the data, okay? And then after that, in the beginning of each iteration, this file is always deleted. And also, as I mentioned, we have a flat for baseline correction coded into SMILE as well. Last thing about sampling schedule, waiting or not waiting. I know that this is there's still a lot of debate, and I want to offer you my spectroscopist view of this. Okay, my perspective. I know it's debatable, so I'm sure that you have different opinion. Here's how I look at it. When I look at some impact, I look at the extreme case. Okay, so in this case, extreme case is that a 50% complete sample, random sampling, and this is a 50% of the first data point, the first part of the first 50%, and the NUS is really completed the second 50%. I set it to 0. And you do fully transform, you see that you see a nice peak. It's stronger, and the artifact level is also lower but coherent. This is really the truncation effect. For this kind of sampling, you can consider the truncation, the sinker wave, as a special NUS artifact, right? And in this case, it's random, more randomly, although it's still symmetrical-like look. And but the amplitude of the artifact is larger, but then the peak is resolved. So any sampling, weighting, depending on how much you weighted, it's in between, right? In between, meaning that you either get better signal to noise and with lower starting artifacts, but worse resolution. And if you do less weighting, you get something like that. So there's always trade-off, okay? And so to me, fortunately, we are more resolution limited than signal to noise limited. So random sampling is mainly what I do for my experiment, and so far it has been working fine. With some of the sampling schedule, for example, Poisson gap, I found actually if you weight them, the peak could be distorted significantly so that SMILE actually perform a little bit less than random. So this is my perspective, and it could be long, and we can discuss about this later. And I guess with this, I want to finish my 2 parts discussion. I want to thank Dennis Toshio for initially formulating the algorithm and test it. And Ed has a lot of support and discussion and very helpful, even with some of the programming stuff. Frank has been very helpful with the C programming and always discuss whenever I need it with me. The postdocs for working, I have a privilege to work with so many postdocs, and the data are presented, all data are presented from these postdocs, and I feel very fortunate and thank them for all the data and the collaboration, of course. And John Louis for some of A beta sample. Dan supports the computers that I've been using. Dusty for managing the machines that I've collected data from field, build the high pressure machine. And thanks very much to the nmrbox team for this platform for me to present, to share my research with you. And if you have any question, or if you want to look at some of the SMILE stuff, we have also a web page, simple, very simple, looks very simple web page. And you also can reach me from there by clicking my email. And I know that more question out there, and if you have some ideas that can help me to improve this, please contact me. Or if you have any questions, anything, or you need help with the processing, or you don't get good data, good reconstruction, please write to me. And I've been always responsive to other users. So sorry, I don't have a latest group of picture. This is a very old one because I couldn't find one. We work too hard. We don't take a picture. We don't have time to take a picture often. So sorry about that. And again, thank you everyone for your attention. I really appreciate it for this opportunity.
Fantastic. Thank you, Jinfa.
Sure, thank you. And I thought that we wanted you to share this partial component tool in nmrbox, right? On nmrbox.
Yeah, sure. The discussion went pretty heavy into the area of random phase detection, partial component sampling. I've got a lecture that I've given in workshops before, and there are video streams and slides available in our June 16th event. But I went ahead and pulled just 2 or 3 slides out. Maybe I'll share those, and then I can show nusttool inside nmrbox, and that'll give people the access to a utility to generate sample schedules that use some of the cool concepts that you just mentioned.
Right, thanks.
So let me go ahead and share screen here. Are you able to are you able to see the screen?
Yes.
Okay. So I figured I'd start off with just a little bit of nomenclature, a little bit of terminology here, just so we're kind of all on the same page. This is typically how we approach looking at a sample schedule, where we've got our indirect dimensions T1, T2. Each point in this on-grid sample schedule, if we're using quadrature detection, would correspond to this bundle of hypercomplex components. Each one of these components, which we use the I and the R tag for each of those indirect dimensions, each combination then corresponds to a particular 1D FID. So the general concept that we put forward with random phase detection comes down to this sort of distinction here. So what we're looking at is a 1D slice through one of those sample schedules. So time is going on this horizontal axis. And then we can think of phase as being an additional axis here that's on the vertical direction. So each slice through this panel corresponds to a collection of FIDs that are all at the same hypercomplex location. So with traditional sampling, which we now call full component sampling, one would either collect all of the FIDs at that location, or they would collect none of the FIDs. What random phase detection introduced was the concept of selecting exactly one at each location, one and only one FID. The more general treatment of that is what we call partial component sampling, and that's where you can select arbitrarily any number of FIDs at each one of those locations, 0, 1, 2, 3, or 4 in the case of 2 indirect dimensions. So with that as a bit of background, and without going into kind of all the other research that comes into play when you start looking at random phase detection, what I thought I would do here then is just give a couple quick comments on nusttool and show people how to access that, and then we can take a look at some sample schedules that make use of that. So everyone should have RealVNC installed on their machines, especially for the tutorials we'll be doing this afternoon. You don't have to follow along with this right now. I'll just show the steps so that way you're ready for later, but you'll be able to see everything on screen here. So I've got RealVNC viewer open. I already have a bookmark for my particular connection to nmrbox. If you don't, then in this bar right here, you can type in the name of the host that you can connect to, which would typically be your username.nmrbox.org. There are other hosts that you can connect to, but that'll be fine for today. And if I connect, I get a virtual desktop over here showing nmrbox. And what I'm going to show right now is something that is reviewed in some previous slides from a presentation I did earlier. So here on the website, here's the June 16th event, and here's a link to the video and slides. And there's also a PDF in here for this tutorial. And that's what I've opened over here in the background. This is a tutorial for using nusttool. So inside of nmrbox at a terminal, we're just going to type nus-tool. And that opens up the nusttool utility for generating sample schedules, writing them to file, loading schedules from file, some analysis tools, and then some settings for the program itself. So what I thought I would do right now is simply generate one sample schedule in the traditional way, which we would call full component, and then I'll enable partial component sampling. I'll write that to file and we can take a look at it. And then that should connect this utility to the work that Jinfa was just talking about. So in this tutorial, I'm going to scroll down to the 6th page here, and this shows the parameters and an example for generating a sample schedule, and I'll just reproduce that right now inside the nustool utility. So we're going to work on 2 indirect dimensions. We're going to have 128 points on the first indirect, 64 on the second. For our sampling scheme, we're going to do exponentially biased, and we can do 25% coverage. Our decay rates will be 175 hertz and 56 hertz along our 2 indirect dimensions, and our spectral widths will be 9650 and 1525 hertz. When we click on the generate button, we get some output as to how many FIDs have been selected. We can plot that sample schedule. We get a view of that right here. And if we go to the right tab, by default, it's going to write this to a sample schedule file in my home folder called nustool-schedule.txt. So I'll just write that to file, and I get the output that tells me it's there. And if I go into the terminal and I run the head command, so that'll show me the first 10 lines of this file, these are the time points that are being collected. So each row in here corresponds to a T1 and T2 time that we see over here in our sample schedule. So now to connect this more traditional approach to non-uniform sampling to what Jinfa was just presenting, if we go back to our generate tab, and under component, if we make use of partial component sampling, now rather than writing one single sample schedule like this when I click generate, what we're going to get is a collection of 4 sample schedules, an independent one for each of our 4 hypercomplex components. So now if we go to our right tab and write that to file, and we come in here and we take a look at that schedule, you can now see that each of the time points comes with a corresponding tags to show which hypercomplex components have been sampled. Now in this case, the sampling coverage is pretty dense, so we're hitting all of those low coverage, those low evolution time points in all 4 hypercomplex components. So let me lower this to 5% coverage. So now it's a little bit more sparse. And if I write this to schedule and we come back in here and take a look, now you'll see that at these evolution times, we're hitting a subset of those hypercomplex components. And as Jinfa just showed in his particular input for SMILE, he wants to take 0s and 1s to indicate the phase or the hypercomplex component of each of those time points. Jinfa, that'll be a trivial change for me to make inside of nustool. I can allow that as one of the output options. So right here in this panel, I'll have a drop-down menu that says SMILE compatible output, and then people can do partial component sampling right inside SMILE from this. I think that'd be really slick.
Okay, thank you.
You bet. Yeah, so that's all I wanted to share. Hopefully that sets the stage for you for a bit later.
Okay. I guess we still have a few minutes for questions for the second part, if anyone has.
Hi, Jinfa.
Yes.
Hi, Rajan here. Thank
Yeah.
you for the wonderful talk. So I have 2 questions. One is this is like a just conceptual doubt I have. Non-uniform sampling, the way we reduce in the indirect dimensions, the total time. Can this concept be is applicable to relaxation time measurements in any way? Can you envisage? Because relaxation time, thermodynamics, there's no way to escape the actual evolution in time.
Yes, actually people do it, right? The question, here's the thing, most relaxation time, T2, R2, T1 low, or test or whatever, is done by 2D, HSQC basically.
Right.
And therefore for 2D, the spectrum is less sparse, right?
Right.
So it really depends on how sparse and your data is. And you're not gonna get like 1% or whatever sparsity level you can get for 3D or 4D. So yes, you could do that. And whether you could do it or not, you could always try by, for example, if you have a fully sampled data set, right? And you can just generate a sampling schedule and downsample it and reconstruct it and ask your own question. Is the reconstruction reasonable? Like how
Okay.
different the two spectrum is. You have basically a true answer, which is your fully sample, and then you have reconstructed one. You can make a comparison and ask yourself, right? And also, you could also try, if you have a high signal to noise series of relaxation data, you could try by yourself just by coming up with a sampling schedule, downsample this and reconstruct them, and you get a set of measurements and compare that with your original measurement. And the question is, are the results agree with each other? Is there any systematic difference or something like that? You can always evaluate it ahead of time.
Okay. Now, I want to clarify my question a little here. Mm-hmm. Typically, in non-uniform sampling, when we do spin labeling, like a time evolution along the chemical shift axis, that is where we try to cut down the time by,
yes.
Right?
Okay.
What I'm saying is something crazier, probably, sorry. Okay, a priori, all of NMR signal is an exponentially decaying signal, we know. As for the relaxation time, probably I'm not supposed to assume that, but suppose I told you, okay, this is an T2 is an exponential decay. Can I sort of cut corners there?
So you're talking about not using the same sampling schedule for each plane, but you using different sampling schedule. Is that what you're saying?
Yeah, something, yeah, like that, yep.
I don't do that. I don't have it. It's not easy for SMILE to do this. And yes, you might get more randomization, but it's not capable of doing that for SMILE. So you really need to do, if you use SMILE, you really need to use the same sampling schedule for every plane. You cannot sample along the curve, but other people do it, okay? Professor Kosminski at Warsaw, University of Warsaw, he used this Laplacian transform.
Okay.
To reconstruct something like that. So I suggest you look into that.
Okay.
And Frank may also doing something similar like this within his NMR pipe, IST methods.
I see. Okay, so at least it is not really an outlandish idea, I suppose, right?
Yeah.
It's not a crazy idea.
No, not crazy. People do it, and in principle, it should give you introduce additional randomization, yes, because you measure with different data points at different frequency, right?
Okay. Yeah.
The same frequency, but you use basically different sampling schedule. So in the end, you probably have more complete information about what you want to measure. Instead, SMILE can, based on the first one, before the signal decay, based on, use the information, frequency and peak width and whatever, supposed to be the most accurate in the first plane. I use that to reconstruct the other weaker decay plane. That, we do, and I have example for that using this RT experiment.
Okay. So the second question you mentioned about, because Topspin 2.1 forces you to hard code the pulse program.
Yes.
So you could easily go and manipulate in what temporally how the actual sampling is done by the program.
Yes.
But does it mean that Topspin 3.x we are stuck there, or because there's no way to compare?
No. We, if possible, use Topspin 3. Use the Bruker standard one. And the reason that we are not very good at it, to be honest with you, I think it's historic. Because we started doing 3D, Bruker didn't even support, okay? So in the early days, when the whole 3D thing started, we run 3D as 2D. And we hard code everything ourselves.
Right.
And then people just got used to it and never really looked into Bruker way of doing it.
Okay.
Now I have pushed hard, try to use Bruker way as much as we can. And it's true that we don't have fine control. If we use Bruker way of coding, then use our own way of doing things. For example, HNCO, all the backbone-based experiments, right? Yeah. The nitrogen dimension is limited by 25 milliseconds because that's how you NCO and nitrogen transfer or rephasing or NC alpha. And that's very bad for the IDP or for a lot of stuff that we need to go way beyond 25 millisecond acquisition time, right?
Right.
So we do something called mixed time. So basically, we ask the question, is there any delay still to be decremented? If it hits zero or before zero, almost zero, we say we don't decrement, instead we increment other delays. So basically what we do is that we run constant time of 25 millisecond. When that constant time that used for, you know, NCO or NCA transfer is over, we hit a negative time. Before we do that, we keep that time and then we start to increment the delay. So the signal doesn't decay in the beginning and then decays. And that you can sample to whatever time points you want. You can get any high resolution you wanted up to natural line width, right? So
Pardon my interruption though, but why don't you include a semi-constant time there instead?
Semi-constant is okay too, but mixed time is better because there's no decay in the beginning. The integral is higher because you don't decay in the beginning. Semi-constant you decays, but more slowly in the beginning, and at the end it hits the end of the constant time, which is fine. Yeah, Bruker does that, but I don't know if Bruker has every backbone experiment running in semi-constant time. I don't know.
It doesn't.
Yeah, it doesn't. So that's a bit of a problem there. Yeah. So if you do this semi-constant time, you're okay. You don't have if condition. But if you do the mixed time that I actually published in 2000 something, I don't know, we did it on RNA first, is that you need a if condition. If D0 is not enough for increment by IN0, then we don't decrement it anymore. We increment something else to run into the real-time increment. So with that, it's very hard to code it in with Bruker standard one, even for top spin 3. And we still prefer our own way of coding it. But I figured out that I could put the if condition in the body of the pulse sequence instead of in the end, in the loop. So I still could use Bruker stuff for doing this kind of thing. And if you're interested, I can send you all the pulse sequence. I'll show you. All right.
So, but again, one small clarification. The reason I asked that question is in relation to, for example, the amyloid beta example you gave, where time dependent, the sample intensity evolves. So you mentioned that the randomized way the Bruker, it generates the null list, but then the way it samples it is not under control, which you could control because you had to code it in topspin 2.1. That was my...
No, you have control too. So with Bruker, here's the thing. If you set the NUS sample to automatic, it automatically generates for you, and it's always random for Bruker. At least I don't know how to control it, okay?
Yeah.
I may have here now by the latest version, but not the version that I use. But if you give a sampling schedule, a name, and put that sampling schedule in the VC directly, it will use your sampling schedule, whatever you do.
Oh.
You use your own, okay?
I see.
So you could still use Bruker pulse sequence, but your own sampling schedule, it's fine, perfectly fine. And I suggest you test it, okay?
I see. So that way you can control the temporal sequence with which the samples are,
that's right.
the points are sampled. Okay.
Right, but it does not do partial components because Bruker pulse sequence has no capability of doing that.
Okay, okay.
But I have an example to show you. It's actually very simple to code.
Okay. Thank you, Jim.
Sure. Thank you.
Okay, if we don't have any other questions, I think we're right up to our break at this point.
Yeah.
Jim, are you still feeling good for 1 p.m.? We'll resume with the demos?
I should be fine, but give me 1 more minute. I thought that it might be good to let people know what kind of data set I have, what I'm going to talk, and let them self decide whether they want to stay or not.
Sure, give them a little teaser.
Okay, so I'm going to share screen my NMR box. So I'm going to open up this. It might be it should be in your data set already. If you go to your data set for today's workshop, there's something called the data info.txt. And I tabulated everything that I want to cover. And I may not have time to cover everything, but at least I'll give you an example. The first one is what I talked in the second part, is the constant time HSQC, and I'll show you how to double the acquisition time as a resolution enhancement. And I'll have a display to show you, three spectrum side by side. The second one is also what I covered to fix the bad FID. And I have a script that helps you to create from the data log. The TopSpin 3 has this data log, like tells you which FID is bad. And for TopSpin 2, you don't have it, and I'll tell you a way how to create the list of FID, and then from there you create a sampling schedule and then run it. And then I have a traditional HNCACB experiment, but this case it's high resolution because the sample is a mixture of deuterated and protonated alpha-synuclein. We want to use this to measure the deuterium isotope effect. So basically, we need NUS to separate two identical protein, but label a slight difference. A high resolution is needed. And so this is traditional HNCACB, but it's an interesting example of having two mixture in the sample. Then I'll give you the example of nosy HSQC in RQD, okay? And I'll tell you some tools that you need to do the experiment. I'll also share with you the pulse sequence and the reconstruction as well. And then another example is the RT experiment. I'll show you how we do this pseudo 4D, because RT is collected as 2 3D, and we reconstructed that as one pseudo 4D. That's the example. Another one is IPAP C13. C13 detected some C13's nitrogen and CO correlated experiment, okay? And this, I want to show you what a Bruker screw up will complicate the data. And it cost me almost a day to figure it out, and needs something very unusual that you probably never heard of it to process the data. It's not a particularly nice data set. The user, David Libich, a professor at UT Texas Health, Santonia, sent it to me. And it's a test data. It's not high quality, but give you a taste of what you get when Bruker make a mistake and how we correct it. And then I'll give you an example of 4D, HMQC, nosy, chosy. We're not gonna run this. I guess I just wanna show you to include this data as a completer, because if you run NUS, you more likely you'll get this 4D at some point. So you see how I do this thing to the 4D reconstruction. Okay, that's all I have for the example. And let's see, we'll